Hey, good morning, everyone. Again, I'm sorry that I'm not able to be there this morning, but I'm thankful that somebody else is taking over. Um, just as a review, today is a short day, obviously. We've got 45, 50 minutes. Um, we're going to be doing a couple homework problems on implicit differentiation. I'll do a little bit of review here, and then we'll move on to a few more formulas for new um, inverse trig functions. I think we talked about one of those last time. We'll do a couple more of those. And that'll finish out for today. Tomorrow is the quiz, and I'll do a little bit of review at the end of today for that. And then finally we'll do a little bit more with logarithms and logarithmic differentiation. So that'll finish out this week. Let me go ahead and open us in prayer, and we will jump into what we have for today. So, God, again, technology is amazing, and we are just so grateful that we're able to utilize it for your kingdom and for your glory here. Thank you that I can be praying here, and my students are there, and together we can lift up your name and lift up our voice to you and just cry out and say, you are an amazing God, and you are truly worthy of all of our praise. We love you and we praise you. And we pray that all that we do today would be a sweet offering to you. We love you and give this time to you. In Jesus' name, amen. So, just as a review, remember that with implicit differentiation, remember the word implicit is the opposite of explicit. So rather than one of the examples we looked at last time, is rather than having an explicit formula for a function, we instead have an equation that defines that function, but it's not solved for y. So here I have an explicit formula for y. Here I have an implicit formula for y. It's implied, but it's not solved for. And one of the things that we figured out is that I can differentiate the equation and get the derivative in a similar way to being able to differentiate when we're solved for y. The nice part, though, is that there are many equations here where we can't possibly solve for y. So we can't get to this step, but we can still figure out a derivative using this process that we call implicit differentiation. And you remember it has two steps right here. So we just differentiate the equation, just straight out, there's the equation, you differentiate it. Then we solve for the derivative. Y prime, dy dx, whichever one you want to use, okay? So I thought I would do two homework questions for you today. And since I can't take suggestions there, I am going to pick 13 and 15. So let me go ahead and go through those. I need to erase here. So section 2.5, number 13 and number 15. Hopefully some of the other ones were very similar to ones that we did in class. So if you have further questions on them, you're welcome to email me and ask me those. But we'll go through 13 and 15 today. So let's start with number 13. So the equation here says sine of x equals x times 1 plus tangent of y. Okay? So here's our first, this is number 13, our first equation. So if we want to figure out the derivative, which is what we're asked for here, the first thing we do is we just flat out differentiate the equation with respect to x. So the first thing we're going to do is differentiate. Okay, so I start on the left side. I'm going to differentiate sine, and the derivative of sine, I just get cosine. Equals, and then on this side, on the right side, I have to do which rule? I have to do the product rule. So I'm going to do derivative of the first times the second plus the first times the derivative of the second. So that should be your next line. I'm not jumping any steps. I'm not trying to do any of those derivatives in my head. I'm just differentiating with respect to x using the product rule. So let's keep going. I rewrite my cosine. Derivative of x is 1. So I've got a 1 plus tangent y there. X, derivative of 1 is 0. Now tangent of y, remember this is tangent inside, tangent is on the outside, and y is on the inside. So y is inside tangent. So we're going to differentiate the outer. The derivative of tangent is secant squared. Then we're going to insert the inner function. And then we're going to multiply by the derivative of the inner function, which is y prime or dy dx, whatever you would like to write that as. Okay? So maybe cleaning it up just a little bit before we try to solve. We've got 1 plus tangent y plus this 0 goes away, and I really just have x times secant squared y times y prime. Okay, and the thing, we talked about this in class, the thing I'm solving for here is y prime. So again, if I sort of think in my head, if everything except y prime were numbers, like if I had 5 equals 1 plus 3 plus 7y prime, what I would do is I would bring these terms over to the other side, then I divide by 7. So I'm going to do that same thing here. I'm going to bring these terms over. Okay, so I'm going to have cosine x minus 1 minus tangent of y, and I leave this other term right there. And then the last thing I do is I take that stuff in front of the y prime and I just divide by it. So I'm going to bring it over to the other side. So I'm going to get cosine of x minus 1 minus tangent of y all over x times secant squared y. And that is my derivative. Okay? Yep, they didn't ask for the derivative at a point. If they asked for it at a point, then I would plug in a point, but they didn't ask for that. So that's it. All right. Hopefully that's pretty clear. All right, let's give one more shot here. Let's try number 15. Okay, so number 15, that one was a little easier because we only had one y prime term. So number 15 is a little more complicated. We've got y equals sine of xy. Okay? All right. So first step is I differentiate, right? I just straight up differentiate. Now remember, y is a function of x. We're kind of thinking in the back of our mind that y is a function of x. So the derivative of y is not 1. The derivative of y is going to be y prime, or dy dx. Whatever that function is, it's going to be that function's derivative. And now here I immediately encounter what rule? I've got the chain rule. So I've got as my outer function sine, and then my inner function is this product xy. Now the product rule is going to come in, but it's not going to come in right away. I deal with the outermost thing first, right? Outside in. So I'm going to first differentiate the outer. So the derivative of the sine is cosine. So I differentiate that outer function, plug in the inner function. So I get xy there, and then multiply by the derivative of the inner function, which is going to be the derivative of xy. Okay, that's something that I still need to figure out, so let's keep writing everything else. Cosine of xy times, so now I've got a product rule here. So I have a product of two things, so I'm going to need derivative of the first times the second plus the first times the derivative of the second. Okay, you may feel comfortable enough now that you can do that all in one step, and that's fine. If we're going to take another step here, I've got cosine of xy times derivative of x is 1, derivative of y is y prime. Okay. So first step done. All of the calculus is done here now. So I've differentiated everything. The only derivatives that are left are the actual ones that I want to solve for. So the second step that I take is now I need to solve for y prime. So the terms that have y prime, obviously this is y prime. There's a term over here that also has y prime. So if you remember, we did an example in class last time where, let me again just substitute some numbers here so you can kind of think through what's going on here. Let's make that cosine some other number. Cosine can't really be 3, but you know, 1/2 times 3 plus 5y prime. So if I was trying to solve for y prime, this was the example that we looked at last time, or a similar example. In order to get all of the y primes on one side, I have to first multiply whatever number this is here onto both of these terms so I can separate them and put one of them on the other side. Right? The first thing I have to do is multiply this out because in order to be able to pull that y prime term onto the other side. So to solve for y prime over here, the first thing I'm going to do is I'm going to multiply the cosine of xy onto both of those terms. So I'm going to get cosine of xy times y plus cosine of xy times xy prime. Right? I just distributed that cosine of xy onto both of those terms. And now I've got a y prime term here and a y prime term here. So let's get all of the y prime terms on one side. I'm going to subtract this one over. So I'm going to get y prime minus cosine of xy times xy prime equals the other term here. Oops, there's no prime there. I need to be super careful of that. Okay, so now I can factor that y prime out. Do that over here. So y prime, so if I factor that out of this term, I just get 1. And if I factor out this other term, I just have a cosine of xy times x. And that equals this other term, cosine of xy times y. And now I just divide that term over. So y prime equals cosine of xy. Usually we like to put variables in the front of more complicated things. So I'm going to write it as y cosine xy over 1 minus x cosine xy. Okay? And that is my answer. Okay, kind of a little more complicated, but it's still doable, right? You just have to visualize what's going on here when you try to solve for y prime. One note I should definitely make here. Please, please, please don't do this. I sometimes see people do this. If I have cosine of xy times y, they'll write it as cosine of x times y squared. Those are not equal. No, 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 no. Don't do that. You can't suck numbers into cosine. Okay? It doesn't work that way. Right? You can't take cosine of pi over 2 and pull the pi out, or stick the pi in. And so in the same way, you can't take y and throw it in the cosine, or take y and pull it out of the cosine. Don't do that, okay? Be super careful. I kept those x's and the y's that are outside the cosine, I kept those separate, kept them away from that. All right. So hopefully that helped answer some of your questions. Again, if you have further questions, you can email me. Okay, so what we started to do at the end last time that I'm going to kind of keep going with is we were using this idea of implicit differentiation to actually get formulas for derivatives of functions that we didn't know how to differentiate yet. So an example that we did last time was arctangent. I didn't quite present it this way, but if I had the function arctangent, and I were to take tangent of both sides, remember tangent and arctangent are created so that if I have one of them and then I put the other one on, that second one dissolves the first. Okay, so these eliminate one another. So these two equations are the same equation here. Y equals arctangent x and tangent of y equals x. So what we did here, we don't know what the derivative is here, but this equation I can differentiate. And so we did differentiate it. And then we ended up with an expression for y prime. Now I'm not going to go through all the steps that we did there. But then we manipulated this so that we just got x's in it. And then that turned out to be the derivative of arctangent. Okay, so the derivative of arctangent is 1 over 1 plus x squared. And this is one of the two inverse trig function formulas that you will have to memorize. So this should go on that sheet, that list of functions that I constantly put on the sideboard. That needs to be on there, okay? All right, so let's do the same concept, but we're going to do it with arcsine instead of arctangent. Okay, so let me erase this here. All right, so I'm going to take the function arcsine, which I don't know how to differentiate that. That's complicated. We've never done that before. And so I'm going to try to simplify this equation by taking the sine of both sides. And again, if I have x and I have arcsine, and then I apply sine to it, those are created, those are inverse functions, so they get rid of one another. They dissolve one another. So these go away, and the equivalent equation that I can deal with instead of y equals arcsine x, which I don't know how to differentiate, is sine of y equals x, which I know how to differentiate everything in there. Okay, so let's do this by implicit differentiation. So let's differentiate this. So the derivative, again, this left side, I have a chain rule. The outer function is sine, and the inner function is y. So I'm going to have to differentiate the outer function. Derivative of sine is cosine. Plug in the inner function y, and then multiply by the derivative, y prime. So that's the derivative on the left side. The derivative on the right side is, the derivative of x is 1. That part's an easy part. So what we get here is that the derivative y prime is 1 over cosine y. Now that's great, I have a derivative, but I want a formula with just x's in it. Just like I had this formula over here for arctangent, we ended up with just x's in it. So what I'm going to have to do, x is related to sine, and what I have here is a cosine. So I have to figure out a way that sine and cosine are related. And thankfully, we actually have a formula that involves that. So the formula that connects sine and cosine is that sine squared plus cosine squared, let's use y's here because that's what I'm actually going to be using in here. So sine squared of y plus cosine squared of y is 1. That's one of those three formulas that I wrote down on the board before. We didn't end up using it, but this comes from the Pythagorean theorem, right? So cosine squared is 1 minus sine squared. All right. So if I could turn this cosine into something like this, then I could use the fact that sine of y is x and get a formula with just x's in it. So the trick here, I'm not going to force you to do this on a test, but it's useful for you to see this here. So the trick is to turn cosine of y into the square root of cosine squared. So if I have cosine of y, if I square it and take the square root, I get the same value back. Now, you should almost immediately be asking the question, well, what if cosine of y was negative? If I square it and take the square root, I'm actually going to get the absolute value. I'm not going to get the original thing back. I'll deal with that in just a second. So I'm going to put a little question mark there right now. We'll come back to that. Okay. But if cosine of y is the square root of cosine squared, so the squared and the square root go away, then if I substitute this formula back in, this is 1 over the square root of 1 minus sine squared, and sine is just x. Sine of y is just x. So this formula turns out to be the square root of 1 minus x squared. And that turns out to be our derivative. That is the derivative of arcsin. So the derivative is 1 over 1 minus x squared. Okay. So now, the one question that I haven't answered is, why can I do this? Why is it that, can I square cosine and take a square root and I get the same thing as I originally had? In other words, why is cosine of y positive? The thing you have to remember here, this gets a little technical, but the thing you have to remember here is if I was talking about the sine function, the way that we got the inverse function for sine, we had to cut it, right? Because this function, if you flip it, if you actually look at the inverse function, if you flip it around that line, y equals x, if you flip it, you don't get a function, right? It's going to go like this. So that fails the vertical line test because the other one fails the horizontal line test. So that means we need to cut it, and the place that we cut it was right in here from negative pi over 2 to pi over 2. That is where we cut the sine function so that we could make the arcsine function. Now what I want you to notice is in that region, when we're looking at the sine function in that region, from negative pi over 2 to pi over 2, the cosine function is actually all positive there, except at pi over 2 and negative pi over 2. That's a different issue, but because it's 0 there. But the cosine function is positive here. So if we're dealing with the arcsine function, the corresponding cosine function is actually always positive. So I can square it and take the square root, and I get the same thing here. So this really is an okay step for me to do. All right. Now don't freak out. The takeaway from this is the other formula that I want you to know from these inverse trig functions is that the derivative of arcsin is 1 over 1, the square root of 1 minus x squared. Okay, it's similar to arctangent, except there's a minus instead of a plus, and you have a square root down there on the bottom. Okay, so these are the two formulas that I really want you to know and remember. Okay, just out of curiosity, it turns out, so I just want to show this to you. I'm not asking you to remember these other inverse trig functions, but the derivative of arcsin is 1 over the square root of 1 minus x squared. It turns out the derivative of arccosine is actually exactly the same, except it has a minus sign. It's exactly the same, except it has a minus sign. And it might be interesting for you to think about why. Try to prove that. You don't have to do that for homework. It's just something to think about. So now the derivative of arctangent is 1 over 1 plus x squared. It turns out the derivative of arccotangent is, can you guess? It's the negative of that. Negative 1 over 1 plus tangent. Sorry, 1 plus x squared. Okay, it turns out that it's the negative of that. Now, arcsecant and arccosecant have some kind of weird definitions, but their derivatives end up being similar to the arcsine function, except the terms are reversed and you actually have an x sitting out front. And the derivative of arccosecant is actually just the negative of that. So x squared minus 1. So that's just kind of, that's for free, interesting stuff for you. You're welcome to kind of log that into the back of your mind. I'm not going to test you on it. It's not super critical that you know that, okay? So but these two are our two inverse trig functions that we absolutely need to know. So you need to remember those. All right? Okay, so that actually takes care of derivatives of trig functions and inverse trig functions. The only category of functions that we haven't yet dealt with are, so we have the derivative, if you remember, we have the derivative of e to the x. That is my favorite function. I'll keep telling you that. But we don't know how to differentiate a to the x, where a is some number bigger than 1, but if it's different than e, how do we differentiate that? So we don't know how to do that. We don't know how to differentiate the natural log. And we don't know how to differentiate a more general log. Okay, so we're going to do 2 of these today, and then I'll save one more for Thursday, and then we'll explore logs, doing derivatives with logs a little bit more on Thursday after the quiz. Okay? So let's start with, the one that I want to start with here is the natural log. And we're going to figure out the derivative here in exactly the same way that we figured out the derivative for arctangent or arcsine. We're going to start with this equation, y equals natural log of x. This is our function that we want to start with. But we don't know how to differentiate this. So we're going to apply an inverse function to get an equation that I do know how to differentiate. And then we're going to use implicit differentiation to just differentiate that. Okay, so the inverse of natural log is e to the x. Okay, so what I'm going to do is I'm going to apply e to the x to both sides. I'm going to take e to the left side and e to the right side. I'm going to apply e to the x to both sides. And these two functions, again, are created if I have x and I apply natural log and then I apply e. They're created to undo one another. So in other words, the e and the ln kind of cancel. They get rid of one another, and I get e to the y equals x. This is an equation that I am much more comfortable trying to differentiate. So we're going to do that here. We're going to differentiate this using our implicit differentiation. So we have a chain rule here. The outer function is e to the x, and the inner function is y. So we differentiate the outer, and that is my favorite function. I love it. E to the x. I'm going to plug in my y, and then I'm going to multiply by the derivative of the inner function. Okay? So that is the derivative of the left side. I'm just using a chain rule. Now don't write equals x. We have to differentiate the right side too, so I'm going to differentiate x and I just get 1. So first part of my implicit differentiation is done. Second part, I need to solve for y prime. Thankfully that's pretty easy here. Y prime equals 1 over, I'm just going to move the e to the y, the other side and divide by it. Okay, so that is my derivative, but I've got y's in my derivative and that looks awful. We want a formula that just has x's in it, like these. And what you'll notice is that e to the y actually equals x, so conveniently, that is my formula. So we get this formula for the derivative. If y equals natural log of x, then the derivative is 1 over x. So this gives us another formula for our list here. The derivative of natural log of x is 1 over x. So natural log may feel like a really not fun function, but the derivative is a really nice function. It's 1 over x. And maybe even it may help to think about the fact that if I had the, remember the natural log function looks like this. Here, right at 1, you can see that the slope kind of looks like 1. The slope gets less and less steep. It never becomes negative, but it gets closer and closer to 0. So the slope gets closer and closer to 0. And if I go to the left, it gets steeper and steeper, so the slope gets higher and higher. So, and this looks exactly like the function 1 over x. Okay, so this is a reasonable answer. If I started with natural log of x, my derivative seems to be reasonable. And we've worked it out with algebra, so that gives us some confidence there, okay? All right, so good. So that actually gives us this formula right here. So the derivative of natural log of x is 1 over x. We are good there. The other one that we're going to try to do is this more general log base a of x. So remember that natural log is log base e. We're going to do this more general log base a. Okay. This will be the last formula we'll do for today. Okay, so in order to do this, there's a couple things that I want to remind you of. First, e to the x and natural log of x are inverse functions. We talked about that. Remember that a to the x and log base a of x are also inverse functions to one another. All right, so what that means is that if I have log base a of x and then I take a to that, these eliminate each other. Or if I take a to the x and then I plug that inside log base a, those eliminate each other. So again, I've got x, log base a of x. If I take a to the x, if I take the inverse function, those undo one another, and I get my original thing back again. Okay, so just remember that's what this function is, the inverse of a to the x. A to the x looks like this, assuming a is bigger than 1. So log base a, if I flip that, is going to look like this. So that's the first thing to remember. Second thing I just want to remind you briefly of are a few laws that we had for logarithms, and I think I reminded you of these when we first did logarithms. We had these log laws. Okay, they were things like, let's see, I think I gave you 4 of them. So if I have a log base anything of xy, that is, let me just erase this for a second, so I've got enough room. There's a way to split that so that it's log base a of x plus log base a of y. So in other words, multiplication on the inside becomes addition on the outside. Do you remember this law? I've talked about this. And then log base a of x over y, division on the inside becomes subtraction on the outside. Okay. Then there was a third one that I gave you that talked about what happens to powers on the inside. When you have a power on the inside, you can actually bring it out front. So log base a of x to the r is r log base a of x. You can bring those powers down. If you have a power inside the log, you can bring it out as a coefficient in front of the log. Okay, these 3 laws are really nice laws for logarithms, and they're things that you should remember. You should remember these. There's a 4th law that I'm going to use that you may or may not have seen. So I want to pull it out and just kind of explain it. So it says that if I have log base a of something else, so log base a of b, and I don't like this base that I'm using, what I can do is I can change the base, but I have to divide by log base, that new base, of the original base. So in other words, if I don't like the base, if I don't want to do log base a, and I want to do log base c, that's fine, but then I have to divide by this other term in order to make this equation work. And I'm not going to prove why this equation is true, but this is a nice equation for changing bases. So for instance, if you had to compute log base 5 of 2, and you had to do that in your calculator, most calculators don't have a way to compute log base 5 of something. So what this equation allows you to do is actually say, well, I don't know how to do log base 5 of 2, but I know how to do log base e of 2, right? That's actually the natural log. So what this equation would say is that that's fine, you can change from 5 to e, but then you have to divide by log base e of 5. So in other words, I would need the natural log of 2 over the natural log of 5. If I did this in my calculator, which I can, I'm going to get that answer. Okay, so this law allows you to switch between different bases. And we're going to use that law to get the derivative of log base a of x. Okay, because what I'm going to do is I'm going to say, I don't know how to differentiate log base a of x, but I do know how to differentiate log base e of x. In other words, natural log of x. I do know how to differentiate that, and these two things are the same, except I have to divide by log base e of a. Okay, all I'm claiming here is that if I had log base a of x, if I had log base a of x and I want to go to the natural log because I know how to differentiate that, I can do that, but I just have to divide by the natural log of a. Okay? Now, one thing I want to point out here is that this thing, a is a constant, a is like 5, or a is like 2. So this thing right here, natural log of a is actually a number. This is a constant. So if I want to differentiate this function, please don't use the quotient rule. Okay? You guys hear me say that sometimes. There's got to be an easier way. And in this case, that constant, 1 over a constant, that's just a constant multiplied onto natural log. So what I'm going to do is I'm going to pull that out. That's just a constant. So in order to differentiate, my constant multiple rule says leave the front constant alone and just differentiate this other function. That other function is, the derivative of natural log is 1 over x. So that gives us our new formula, 1 over x natural log a. So the derivative of log base a of x is 1 over x natural log of a. Okay, so we now have a formula for how to differentiate natural log and log base any other base. Okay, and one of the things I want to point out here is that if a happened to be e, in other words, if this was the natural log, log base e of x, which is natural log of x, what I would end up with here is 1 over x ln e. In other words, what I would end up with is 1 over x log base e of e. And that number is actually 1. Because log base e of e means what power do I take e to get e? And that is 1. Remember that we unraveled, when we tried to solve inverse functions, we unravel what they're asking. So in other words, if I plug in e here, I get 1 over x, which is the original answer that we had. So these two formulas match, which is good. We want things to match in mathematics. We want things to be consistent. Okay, so we've got our 2 new inverse trig function rules and our 2 new logarithm rules. We will review those 2 rules and look at this final rule on Thursday and take a little bit more look at logarithmic differentiation. Your quiz tomorrow is going to cover product rule, quotient rule, chain rule, and some combination of those. So remember that you always work from the outside in. So it's going to involve a combination, potentially a combination of those. And then an implicit differentiation problem, kind of like the ones that we had on the homework. Okay? If you've got questions, you're welcome to email me. This lecture will also be available online. I'm putting it on YouTube, but it's available through RenWeb. So if you want to review any of this information, you're welcome to do that. You will not have natural log or other logs on your on the quiz for Thursday. We won't do that. No inverse trig functions on the quiz for Thursday. None of that's on there, but you do need to know those formulas as we move forward. Okay? Have a great service day. Serve others as you would serve the Lord. Be lights out there, and I will see you guys tomorrow. Thanks so much.